Hello and welcome. Introduction. Now, in this video, I'm going to show you how to control the RGB LED on the Tiva C LaunchPad board. So here is the RGB LED. Let's zoom in. So this is the RGB LED, and I'm going to show you how to control this LED in this video. So before we do that, let's remind ourselves where the RGB LED is located. So here is the schematic of the Tiva C LaunchPad board. I've taken this from the Tiva C series TMC 123 datasheet. All right, so basically, here are the RGB LED. So the red LED, which is this one here, is connected to PF1. That is port F bit 1. All right, and then the blue LED is connected to PF2. That is port F bit 2. And then finally, the green LED is connected to PF3, that is port F bit 3. So here is the program in the ARM Cortex assembly code that I'll be using to control the RGB LED. So here is the main program, and this is the subroutine. Now, I'm going to divide the program into 3 parts to explain how it works. So firstly, I will look at the registers that are being used in this program. Then secondly, I will look at the main program. And then finally, the subroutine. So in this part of the video, I'm going to take a closer look at some of the TM4C 123 microcontroller GPIO registers. So let me get my pointer. So this is a diagram of, or rather a block diagram of the TM4C 123 digital I/O pad. And I've taken this diagram from the data sheet. All right, so the first thing I want to highlight is the data register and the direction register, which is these two here. All right, so here and then I would like to highlight this other register, GPIO DEN. That is the digital enable register. And then the other register that I want to highlight is this one here, the GPIO AFSEL. That is the GPIO alternate function select register. All right. And then not forgetting the clock gating control register. Now this register is in the system control block. All right, let's zoom in into this block. All right, so the clock gating control register is located in the system control block. Now, the clock gating control register is used to control the clocking for the GPIO modules. Right, so it has a base address of 400F E000. The offset for this register is 608. So in hexa. So if you add 608 hexa to the base address, you will get a resultant address of 400FE608 hexa address for the clock gating control register. All right, let's zoom in into the register here. And also in this example, I'm setting bit 5 to a 1 because I want to enable the clock for port F. So a 1 will enable the clock for that particular port. Now, these ports here, port A, port B, port C, port D, and port E, they are set to 0. They're clear. That means the clock is disabled for these ports. Now, if you want to use port D, then you will have to enable the port D bit 3 and so on. So in this case, we are only interested in port F. So I set bit 5 to a 1, and that would be 20 hexa. Now, before we go any further, let's quickly remind ourselves of the pin out diagram here. And then let's look at pin 52 of the TM4C123 chip. Now, pin 52, if you look at it, is a GPIO pin for port C bit 0. But it can also function as a TCK. What TCK stands for is test clock. Or it could function as an SWCK, that is a serial wire clock. So there are three possible functions here. So this is where the alternate function select register comes into play. So the alternate function select register has a base address of 40025000. Okay, so at this point, I need to explain this APB and AHB. Now, APB here stands for Advanced Peripheral Bus, and AHB stands for Advanced High Performance Bus. We will be using the APB, Advanced Peripheral Bus. So the base address would be 40025000. All right, so we add the offset to the base address here. Then the resultant address would be 40025420. That would be the address for the alternate function select register for port F. Okay, so let's zoom in here and extract it here. So if the bit is clear, all right, that means set to 0, that pin will be used as a GPIO pin. If the bit is set to a 1, then you configure the GPIO pin for some other peripheral like I squared C or the test clock pin as we seen earlier. All right, so if it for GPIO we need a usage, we will set these bits to 0. Here's an example where all the bits are set to 0. That means we're using all the bits as GPIO pins and the hex value bit 00. The next register is the digital enable register. Now the purpose of this register is to allow the pin to be used for digital input-output operations. So let's focus on bit 0 to bit 7. All right, so let's zoom in here. So to use the pin as a digital input or output operation, the corresponding bit must be set. So let's have a look at this example. So in this example, bit 1, bit 2, bit 3 are enabled because they're set to a 1. So what that means is that these bits are enabled and you can use them as digital input or digital output function. So in this particular setup here, we have this will be 0 in hexa, and this would be E in hexa. So the hex value is 0 E. Next we come to the direction register, and here the base again for port F is 4002 5000, and the offset is 400 hex 400. At the offset to the base, we will then get 400-25400 hexa. That will be port F direction register. All right, let's zoom in on these bits here. So setting a bit in this register will set the corresponding pin to be an output. If you put a 0, that means you clear the bits, then that bit would be an input. By default, they are all inputs. That means they're all zeros. So let's take a look at an example here. What that means is bit 7, bit 5, bit 3, and bit 1, they are now outputs. And in this setup here, the hex value will be AA. The next register is the data register. Now the offset again is, no, sorry, the base is 4002 5000. The offset is not 000 as stated here. It should be 3FC. So you add this 3FC to the base, then we'll get 253FC. Now, this is not an error in the datasheet. The 3FC hexa comes from something called bit banding. In bit banding, each of the bit of the register has a unique address. Now, I will not be going into the details of this in this video. So, but let's zoom in on these bits here. All right. So the data that is written onto this register would be then transferred onto the physical pin of the GPIO. All right. So if we have this example, then physically this ones here, this data itself will be presented on the physical pins. So if there are LEDs connected to this position, those LEDs will be switched on. All right. So in this case, the hex value, all right, this would be 9, this would be 8. That would be 98 in hexa. Here's the code for the main program. Let's take a closer look at the main program, and I'll start off with this part here. Let's zoom in. So area is a directive that defines or set aside a section of the memory to store the code. Now, my code, which is this one here, is a name given to that area. Now, it doesn't have to be my code. It could be any other name that you wish to put in. Then code is an attribute, and this attribute specified for the area. It says that the area contains executable instructions. Read-only is another attribute for the area and specifies the contents in that area is read-only. All right, and then align equals for arrange the code on a 4-byte boundary. And then entry is a directive that is used to mark the entry point of the program. More on that as we go further down the program. And export is another directive and is used to make symbols or labels such as this one. Make this label as accessible by other assembly files or modules. Okay, so here is the entry point, which is __main. And then here, this proc is a short for procedure, or it marks the start of the procedure or routine, sorry. Then BL, all right, that stands for branch link, and basically is used to branch or jump to a subroutine or another procedure. Now the name of this subroutine in our case is set port F. We'll come to this subroutine in a few moments. Now let's look at the first instruction in the main program. Is an LDR. That's load register. And LDR is a pseudo instruction. Basically, it copies or loads a value into register R1. The value that we want to load is already defined here in the earlier part of the beginning of the program, and basically we define that in the equate section. So the value in this instance is 400253FC in hexa. And then the next one is a MOV instruction, basically very similar to LDR. It copies this value 04 hexa into R0. Next instruction in the program is the store instruction. Basically, this instruction will store the contents of R0 into an address pointed to by R1. All right, so whatever R1 contains, that's the address, and the R1 is basically saying go to that address and store that contents of R0 at that address. Basically, that's the address in this particular instant. Then this instruction B stop. B stands for branch, and basically in this case is an unconditional jump. All right, so it will jump or branch to this point, so the program will stay here when it comes to this, when this instruction is executed. And then finally, to end the proc, we have an ENDP, that end procedure. Hey, so before we go any further, let's take a step back and look at the overview of the program. All right, so we start with this instruction here. This is BL, branch link. Basically, this is a branch to the subroutine, or in other words, call the subroutine set port F. And here, basically, these three instructions here basically turn on the blue LED. And this is the code here. I'll show you later on in the code demonstration how to turn on the red and the green LED by changing this value here. So basically, to repeat myself, these three instructions will turn on the blue LED. And then this instruction here, which is branch to stop, this is basically an unconditional jump to this spot here. So the program control will stay here. Now here's the code, the entire code for the subroutine. And basically the overall function or purpose of this subroutine is to initialize, or another word for it is prepare port F. All right, that's the whole purpose of this subroutine. Basically, the code used here is the same as the one used in the main program. You'll see why in a minute. So let's go zoom in to this part of the subroutine first. All right, so we have the name of the subroutine here, set port F, followed by the PROC. This is to indicate the start of the procedure or the subroutine. Notice the next three instructions, LDR, MOV, STR, store. These are the same as in the main program, but let's go through it. So LDR, load this register or copy into this register R1 with the value, this value here, which was defined in the beginning part of the program, and that has been defined with the EQU, and it has the value of 400FE608. Basically, that's a hexa, that's an address. So you copy that into R1, and then the second instruction, MOV, copy this value 20 hexa into R0. And then the third instruction, STR, is the store instruction. Basically, what this does is it stores the contents of R0 into the address pointed to by R1. So where's R1 pointing to? It's pointing to 400FE608. So basically, it will store the contents of R0, which is 20 hexa, into this address. The purpose of this three instruction is to enable the clock for port F. Notice the next four instructions are no op. NOP stands for no operation. Basically, these four no op instruction will generate a delay between activating the clock and setting of the port registers, which is coming later in the program. And basically, this is to allow time for the clock to stabilize. Okay, so notice the instructions are now repeating itself. So let's look at this one here. This one is basically the alternate function select register. So basically, we are going to like set port F for GPIO operation. So LDR R1 with this value, which is defined earlier, which is this value here, copy that, load that into R1, and then we have an MOV R0. Basically, we're copying 00 into R0, and then we have this STR store instruction. Basically, we're storing the contents of R0, which is 00, into the address pointed to by R1. Where is R1 pointing to? Is pointing to this address. Basically, that will set port F for GPIO operation. And then here we have an LDR R1 with this value. All right, copy that into R1, and then copy this value 0E into R0. And then And then the store instruction here will store the contents of R0 into the address pointed to by R1. Basically, this will enable the digital functionality of the port. Then the LDR here with R1 will load the address, this address, into R1, and then we store this value 0E into R0, and then store the content of R0 into the address pointed to by R1. So R1 is pointing to the here. Basically, this 0E will set the direction of these 3 bits. Basically, we're setting these 3 bits for output mode. And then this instruction here, BXLR, that's a branch indirect. Basically, we're using this BXLR to return back to the main program. All right, and then here we have E and D. P indicate that this is the end of the subroutine or procedure. And then finally, this last E and D here signify the end of the entire assembly code. So let's summarize the operation of the subroutine. Firstly, on the first step, we need to enable the clock for port F. So this is the run mode clock gating control register. So bit 5 have to be set to 1. That will then enable the clock for port F. The rest of the ports are, the clock for the rest of the ports are disabled, and the hex value is 20. Next, we need to set the port F for GPIO operation. And here we need to, what we need to do is to go to the alternate function select register, and we set all the bits to 0, clear them, so the hex value is 00. That will then set port F for GPIO operation. Thirdly, we need to enable the digital IO function of port F. So we need to go to port F digital enable register, and what we do is we set these 3 bits, bit 1, bit 2, bit 3 to 1. Together that would be OE in hex. The reason for these 3 bits because the RGB LED is connected to these 3 bits. Then we need to set the direction of the pins. So in this case, we need to set these 3 bits to 1. So that it's the 1 indicates that these 3 bits are set to output mode. The rest are inputs, and the hex value is 0E. So these are the steps we need to take to initialize port F. Hardware requirement. Now for this demonstration, you will need the Tiva C series LaunchPad board connected to your desktop or laptop. Let's remind ourselves where the RGB LED is located. And here is part of the schematic diagram, which I've taken it from the Tiva C series TM4123G LaunchPad Evaluation Board User Guide. And it can be found on page 19. And coming down here, as we can see, the red LED is connected to PF1, which is port F bit 1. The blue LED is connected to PF2, which is port F bit 2. And then finally, the green LED is connected to PF3, which is port F bit 3. So if we look at this diagram here, we know from a few moments ago, I mentioned that the LED, the red LED is connected to bit 1 of the of port F data register. So if you look at the binary pattern here, that would be 0, 0, 0, 0, 0, 0, 1, 0, and that would be 0, 2 in hexa. Now for the blue LED is connected to bit 2. So the binary pattern here in this data register would be 0, 0, 0, 0, 0, 1, 0, 0. That would be 0, 4 hexa. And finally, the green LED is connected to bit 3. So the binary pattern here is 0, 0, 0, 0, 1, 0, 0, 0. That would be 0, 8 in hexa. Okay, so we are now in the Kyle Microvision IDE. I have uploaded the code onto the Kyle Microvision IDE. Now, in this demonstration, I assume that you know how to create a new Microvision project and that you know how to input the code, compile the code, and so on. Now, if you're not familiar with the process, then I would recommend that you refer back to my previous video where I talk about in detail how to create a project with Kyle Microvision IDE and how to compile it and how to download. Alright, so for this particular demonstration, I'm going to assume that you know how to do that. So here is the code that we discussed in detail earlier. So I'll just briefly go through the code with you before I download the code to the Tiva C series board. Alright, so here are the registers that we spent quite a bit of time talking about it earlier. Then from here is the main program. Alright, here these 3 lines of code will actually turn the blue LED, no, in this case is the red LED. No, sorry, the green LED. So 08 is the green LED. Alright, and then from here, this part, the set port F procedure or subroutine. This is the, sorry, I'm repeating myself, the subroutine here. Alright, and this is this to signify the end of the entire assembly code file. Alright, so I'm going to go to project. Alright, and I'm going to do a rebuild all targets because I've done it before. I can also use this if I wish to, so either one will do. So I'm going to use rebuild all target files. Notice I have 0 errors and 0 warning. Now, so now I can download the code to the board. And before I do that, here's my board here. I assume that you have connected the board to your laptop or desktop. In my case, I've connected it to my laptop. So it's ready. So what I'm going to do is I'm going to adjust this a little bit. So that we can see it. Alright, so I'm going to click on this download button here, and it should download. And it says that the programming is done, verify OK, so it's done. So what we need to do now is to press the reset button here, this one here, and the green LED is switched on. All right, see the green LED here is switched on. Now, let's try and turn on the red LED. Now, for the red LED, we need 0, 2 here. So change that to a 2. Save it. Now, any changes that you make, you need to save it and then go to Project and rebuild all target files. Again, there's no errors. So going to download the file to the board again. Alright, so it's done, programming is done, verify OK. So what I'm going to do is, again, I need to press the reset button. And now we have the red LED turn on. Right. So let's try the blue LED. So blue LED, we need to change this to a 04. All right, save it. Go to Project, rebuild all target files. 0 error, 0 warning. And then we download the file. It's done. Verify OK. Bring the... Alright. So press reset again. And now we have the blue LED turn on. Alright. So this is how we can control the RGB LED. Okay, so that's it for this video. Thank you for watching, and I'll see you in the next video. Bye!